Okay, can people in the back hear me? Great. Okay, sorry for the late. Somehow I cannot open my Zoom today. But anyhow, I managed to record the lecture with PowerPoint presentation. So today we will go over the topics which will be covered in our midterm 2. And so far we have finished our lectures on mass transfer coefficient, on mole balance, fixed first law, fixed second law, mass transfer coefficient, and thermal review. But thermal will not be in midterm 2. So instead, whatever is before thermal will kind of be covered in this exam. Okay. Then hopefully today, after we gone through the topics, then if we have time, we can go over. I posted a practice exam on Canvas, so if you get a chance to look at it, if you have questions, we can answer questions about that exam. But be mindful that the same type of problems are not guaranteed to appear in this year's exam, right? The sample exam is just to designed to give you a sense about what will be covered and what type of problems you will expect in your exam. And next Monday it's holiday, and next Wednesday we'll spend a little bit time to just discuss homework 4 a little bit. Right? I won't give you solutions because it's not due yet, but I will answer your questions, maybe give you some hints. Like last exam, ideally I would recommend you, finish homework 4 before exam. At least, go through the problems, try to ask yourself if you can solve it, right? If so, what type of equations are you going to use, right? So you don't have to refinish the homework and upload it, but at least you go through it and think about it and see if you can solve it. Okay. Midterm 2 will have kind of the same format as exam 1. We will have part 1 and part 2. Part 1 will be multiple choices, 6 problems. Well, this time I will indicate how many correct answers are there in for each problem in the exam sheet. Part 2 will still be calculation and analysis. Again, there will be 2 problems. And this time, let's make it all closed book, right? Just to save you effort. You don't have to bring a whole lot of different stuff. Just bring 1 page of notes. Okay. Everybody is the same. And a calculator. Questions?
So 1 page front and back?
Front and back, and with any font size you feel comfortable, right? As long as you can fit in all the things you think are important. Again, in the exam, I'm not gonna examine how well you can memorize equations, right? You don't have to memorize the solution to the Losch tube, right? And you don't have to memorize kind of like the solution to the fixed second law, the ordinary differential equations given different boundary conditions. That's really not the takeaway from this course, right? Those should be learned in your math class, right? If in the exam we need those solutions, I will give it to you in the exam, right? But we have some equations that kind of are important to this course, like the how do you compute the total flux, right? And how do you compute? How do you derive, say, total flux based on mass transfer coefficients, right? How do you derive, make that connection? On what assumptions you can simplify your mole balance equation to fix second law, right? Those, I think it's fair, like you should remember those equations and remember how it's derived. It's not that complicated, right? And it's really the essence of this course, the equation and the physical meaning and assumptions behind those equations. And you should be very proficient at using them to apply them to solve different type of problems. Okay, so I'll go over with you some of the key concepts, right? So, but again, after this lecture, go back and review all the lecture notes and make sure you understand all the concepts and equations. You can derive them and you feel comfortable using them for given conditions so a student came to my office yesterday asking me about tips for preparing for the exam. What I told him is that you may feel like the lecture notes is kind of like disconnected from the homework problem, but really I think the connection is really for you to do that connection, right? Because the homework is given for you to practice how to use those equations, and then the homework solutions provided for you to examine how well you can use those equations. When you prepare for the exams, ask yourself that what if, for the homework problems, right? What if I change this condition to another, right? I change the boundary condition. I change the, for example, for the tank flow problem, what if I add a reaction? What if I, change the flow rate to be a function of something, a function of time? How would the result be different, right? So just ask yourself this question, pick your mind, pick your brain, and see if you can still solve the problem, apply the equations we've learned in our class, solve the problem. If you can do that, that means you really understand the concepts well, and the knowledge you have learned is versatile. You can apply it to kind of any problems, because in the end, you are taking this course as a chemical engineer. In our class, all our problems are man-made and has to have a solution, right? Otherwise, you won't be able to solve it. And me as the instructor and the TA as we won't be able to grade it and give you a score. But this kind of like teaching method, I think it's kind of fundamentally flawed, because in real world, a lot of times the question or the problem is not like deemed to have only one solution. Most of the time it's open, right? So, and it's you as an engineer who should be responsible to kind of define some of the boundary conditions or define some of the conditions and solve the problem, okay? So, well, really you should try to do that, and I'm pretty sure you will be able to do very well in the exam, okay? So we spend a lot of like our time just to talk about fluxes and how do we compute fluxes, in different conditions for a mixture. Then geez, this is okay. So we've learned like total flux is made of like convective flux and diffusive flux, right? And we should be very proficient at converting the fluxes with velocity. So starting from this equation, for a mixture with, if we focus on one component, for example, component A, then the total flux is made of two components, the convective flux and the diffusive flux. And convective flux is the mole fraction of species A multiplied by the total flux. Okay. So, and it's also the flux of A is also the concentration of A multiplied by its own velocity, right? And its own velocity is can be broken down into two parts. It's made of the average velocity of the mixture plus a difference, a difference like the relative motion of the species relative to the bulk fluid flow, and that's the molecular diffusion, right? So if you kind of multiply this with each term in this bracket, you have this CAVM plus CAVA diff, right? And that's your diffusive flux, and that's your kind of convective flux, right? And CA can be written as XACVM, right? So be very proficient at using this, because you will be using it to solve some of the problems. And then we talk about two simple cases, two simple problems. The first one is two-bulb problem, also termed as equimolar counter-diffusion, where you have two bulbs connected by a tube, right? We've discussed in our lectures under the steady state assumption, how do you derive the flux? Let's see, at the beginning you fill left tube with species A, a right tube with species B, and then at t equals 0, if you remove the wall separating these two bulbs, you will have diffusive flux happening in the tube, right? Species A will move to the right, species B will move to the left, right? Then how do we solve for XA as a function of t, or CA as a function of t? Similarly, how do you solve XB as a function of t, CB as a function of t? Okay. And how do you derive the flux of A in the tube, right? Under steady state assumption, we have proved that NA throughout the length of the tube, right? If this is Z, this is Z equals here is. So here's equal 0, here's the equals L. So we've proved in our lecture that under steady state condition, NA is not dependent on kind of location in the Z direction, right? Because at a steady state, your concentration profile is going to be linear, so the flux will be the same across the tube. But that doesn't mean it's not a function of time, right? Because we derived that the flux is still going to depend on the concentration difference between these two bulbs, right? And if we let A freely flow in, diffuse into B, into the bulb at the right, and we let B to diffuse freely into the bulb at the left, then gradually the concentration of A in left and right bulbs will change, right? So then you will have a changing flux, right? Then you need to know how to, based on those assumptions, you need to know how to apply the integral mole balance equation, make certain assumptions, then solve for XAT, CAT, then you can solve for NA as a function of t, right? Now with NA as a function of t, right, based on this equation, well, in this case, there's no flow. Then you should be able to solve XA, right? Solve for XA. Similarly, you get XB here, and solve for JA, JB. Oh, sorry, not XA, VA. VA, VB, right? Then compute VM, right? So kind of really, with this problem, you just use all of your equations and solve everything about the system. And then once you have the solution, ask yourself, does the solution make sense? And what's the physical meaning of the solution, right? If you get a concentration profile change, I mean, in your homeworks, in your homework 3, problem 3, you kind of solve the concentration as a function of t, and you find out it's basically depends on time exponentially, right? It's decay exponentially. So ask yourself, does it make sense? And the concentration profile in the tube is a linear function. Does it make sense? Okay. Also ask yourself, right? What if I change some of the conditions, right? What if you have a tube that's not rectangular? I mean, not the diameter of the tube is not constant. What if you have a tube that's a cone whose diameter is like depends on the z direction, you know, location? And what if you have, you know, the two bulbs have different size, right? What if you have a huge bulb A, very small bulb B, right? That means, well, in given time, maybe the concentration change in the bulb A can be assumed to be, I mean, the concentration of A in bulb A can be assumed to be invariant, right? Because the reservoir is just so big that the flux just creates a very small impact on the concentration of A in bulb A, right? And what if you have a reaction taking place in this chamber in which, for example, you have a reaction converting A to B with a reaction rate of K, right? We've solved this problem in one of your homework problems, right? Just try to ask yourself this question, you know, when you modify the boundary condition, can you solve it? If you cannot solve it, at least, you know, try to derive the equation and see what you can get, right? And ask yourself, well, I plug in all the conditions, I get this equation, then I kind of cannot go further. What do I miss, right? What condition do I need to further solve this equation, right? So that's the equimolar counter-diffusion problem. And then we also discussed the Baker problem, which is also called unimolecular diffusion. In this case, basically, or in the two poles problem, component A diffused to the right, component B diffused to the left. So you have both species diffusing, right, at steady state. But for the Baker problem, it's kind of slightly different. You know, so you have species A, which is liquid evaporating and entering the air. Meanwhile, you have species B, typically this is air, diffuse down, and trying to dissolve in, you know, species A and making a mixture. But at steady state, we demonstrate, right? Once A is saturated with B, right? Once we form a saturation solution of B, then NB here will be 0, right? So then this NB here is also 0, right? Then when you apply this equation, right? So because it's a binary mixture, where we have n, total n is NA plus NB. Well, in this case, because NB is small compared to NA, this is close to NA. Right, and if you plug that into this equation, that just gives you some convenience that we kind of like we can use Fick's law, a modified version of Fick's law, to solve for the total flux of NA. Right, even though in this case we have actually flow. Right, we have the this NA has two parts, both diffusive flux and convective flux. Right. And similarly, right, ask yourself, right, how do I solve for, well, in this case, xa as a function of t, c as a function of t, and here xb as a function of t, cb as a function of t, right? What if you start from a mixture of a and b, right? Let's say, if this is not air, right? Let's say if this is something, this is water vapor. And this is a mixture of water and ethanol, right? Well, let's see, not water vapor, right? Let's see. Well, we can see still water vapor. What would happen? Right, just ask yourself these questions and see, pick your brain, see if you can, apply what you've learned to solve these problems, right? If not, ask yourself, what do I miss? What conditions do I miss? What else do I need to know in order to really fully solve this problem? Okay. Briefly, just review. We introduced Fick's law. Yes.
So, like going back to that beaker problem, is that even unimolecular diffusion as soon as we add another species that's also differentiated?
If you add another species in the liquid phase?
Like if we have the water ethanol mixture and it's water vapor, is that even a unimolecular diffusion problem?
Nope.
So do we know how to solve that problem? Or should we know how to?
I mean, this is what I ask you, right? So assume you have this problem, right? And write down all the equations you have learned so far. And if our end goal is to solve for, we have a mixture. We want to know how does the composition of the mixture evolve over time, right? And then we have mole balance integral and differential mole balance equation, right? We know accumulation equals net influx plus reaction, right? And for each component, write down the equation, right? Make some assumptions. See if you can simplify the equation to a degree that you can, to an ordinary differential equation, for example, you can solve, right? Either analytically or numerically. If not, then ask yourself, do I have other conditions? Do I have the boundary conditions? Do I have initial conditions, right? And this is just to simulate that real engineering problem, right?
Like, how would we solve that problem? What would our boundary and initial conditions be?
Yeah, that's the question you need to think about, right? Like,
I guess I don't know how to solve it if we've not gone over it.
yeah, so if you don't have the boundary condition, then you can ask yourself, oh, maybe I need one more boundary condition. I need one initial condition, right? Then you can say, well, if the boundary condition is this, then the solution will be that, right? So this is just to pick your brain. You assume your problem is an open problem, not a closed problem, a man-made problem with solutions.
Okay, so I'm confused, like why we can't go over it now as part of the review unless it's going to be on the test. Like unless that's a question that we're getting at.
Well, I cannot just, first of all, I haven't made the exam yet, exam problems yet, right? So I can really not tell you what will be in the exam or not. What I'm telling you right now is how I'm gonna make the exam. How am I gonna make the exam is like, I'm gonna start from what you know, what you have learned in your homework, in your lecture notes, right? Assuming, right, if you finish the homework, if you study the homework solution, you already got some good knowledge about how to solve, you know, the ball problem or the bigger problem with this set of conditions. Now I'm going to change the condition a little bit. Then can you solve it, right? So you're going to still use the same equations, but then now, you know, just like our exam one, right? So for the tank problem, you're going to start from the same equations, but now the conditions has changed. Then during the derivation, right, when you simplify the equation, you're going to drop off some terms, but the terms you're going to drop off in your exam problem will be different from your homework problem, right? That is your that is you know, that depends on your understanding of the topic, right? Which is something I cannot tell, because then there's no point of making the exam if I already reveal how you solve this problem, right? I can discuss the homework problem with you. I can discuss in general what would be the methodology to crack a homework problem or a problem of this type. But I cannot possibly give you the solutions to all the problems, right? Because as an engineer, once you graduate, once you get your BS degree, you leave here, you are on your own. You cannot. I mean, if you work for let's say engineering company and you are given a problem to solve, and you cannot go back to your college professor's office and ask him, Professor, can you tell me how do I solve this problem? You haven't taught us this. You haven't really, you know, teach me how to, you know, solve this type of problem, right? Does it make sense?
It just feels like we came here to learn how to solve a problem, though. So we haven't really gone over how to solve that specific problem, and it seems like there's enough problems that could be on the exam that we could go over the solution to that example without crossing over.
Well, maybe I can come up with a fake problem in next lecture and show you how to solve it, right? Just give you another example. But again, that problem will not be in the exam. Does it make sense? I can come up with another fake problem.
What I'm saying is, like, unless that problem that you just came up with is in the exam, I don't see why we can't go over the solution to it right now.
Mm-hmm.
Or talk about like the boundary and initial conditions that it would have.
Okay, I will come up with a fake problem for our next lecture. Okay, then I will go through. I mean, go through how we solve it. But again, I think the important thing here is to, with all these exercises, you know, homework exercises, midterm 1 exercises, you know, lecture problems. Really, what you need to learn is the kind of the mindset. You cannot possibly solve every problem, but if you master how to, you know, logically kind of like formulate each problem, then at least you have the means to, you know, kind of rationalize the problem to be something similar to what we have learned. Okay, anyway, So I guess I will design a fake problem other than the midterm 2 problem, just to give you a sense about, you know, how to do this. So we need to hurry up. Then we talk about Fick's law, right? Which is a model we use to solve for diffusive flux when we talk about its physical meaning, and in which the mole fraction gradient or the concentration gradient is the driving force for diffusion, and the kind of the diffusivity is type of like the resistance or inverse of the resistance for mass transfer, right? If you have a high diffusivity, then your diffusion is fast. That means the resistance for diffusion is low, right? And we apply the Fick's law to solve for the 2 bulbs problem and the Baker's problem, right? Well, that's in the lecture notes. And then we discuss Fick's second law, in which basically we emphasized Fick's second law is like a simplified mole balance equation when you have several assumptions, right? And you need to know what assumptions we made when we derived the Fick's second law. That includes, so we start from differential mole balance equation, right? So if you remember, we start from this. We have the partial differential C over T equals the divergence of NA plus SA, right? That's a differential mole balance equation, right? Then we also have Fick's law, where if for species A, the diffusive flux is proportional to say concentration multiplied by diffusivity multiplied by the gradient of A on the mole fraction of A, right? So we start from this. Then if there's no reaction, this term is dropped, right? And if there's no flow, then total mole flux equals to the diffusive mole flux, right? That's when we can just plug in that term, right? But we can drop the minus sign because we have 2 minus sign, CDAB, right? Then we have the divergence of this whole term. And if we assume that diffusivity is a constant and the concentration of the system is a constant, which does not change over time, and the space, these 2 constants can be taken out, right? Then we can convert this to be C right? Then because C is a constant, you can just drop it out, right? You have this. That gives you the Fick's second law, right? As you can see, we made several assumptions, right? No reaction, no bulk flow, constant concentration and diffusivity, right? And if these assumptions do not hold, then you cannot use Fick's second law. You still have to use the more general form, either the differential form or the integral form of mole balance equation, right? But anyhow, we use this equation to solve for the Loschmidt tube problem and ground contamination problem, right? So in the Loschmidt tube problem, so what we have is like, we have a, component A with different concentration in the left and the right, right? Say at time equals 0, we remove this wall and we let diffusion to happen, right? Then in this case, there's no reaction, there's no bulk flow, and we can apply the fixed second law, right, to solve for the concentration profile or the mole fraction profile as a function of space and time in this problem, right? But since this is a ordinary differential equation and with like space in the second order, we need to have two boundary conditions and one initial conditions, right? And the initial condition would be, we need to know the initial concentration in the left and in the right half of the tube. And in the Loschmidt tube problem, the boundary condition is that we have zero flux at the wall, right? This is the closed tube. Then you can solve this. So you don't have to memorize the solution, right? Because that's well documented in some math books. But you need to understand, the boundary condition. I mean, we need to have one initial and two boundary conditions to solve this problem. And for this Loschmidt tube, the boundary condition is that we do not have flux here, right? And if you have other condition, right? For the two bulb problem, if you add a bulb here, then the boundary condition becomes that we have a kind of fixed concentration here and fixed concentration there, right? Then the solution will be different. And we have a ground contamination problem, which is basically a semi-infinite diffusion problem where you have a reservoir of concentration A here. Then this A species is diffusing into this semi-infinite space, right? In this case, the initial condition in this is Z, right? This is Z equals 0. Initial condition is that in the is CA of Z is 0, right? In this region, when Z larger than 0, your initial concentration is 0. Then boundary conditions are two, right? One is on the left, you have a fixed concentration. On the right, at infinity, you have 0 concentration, right? And you can solve for it. So here, what you need to understand and remember is first the assumptions to get fixed second law, and secondly, when you apply fixed second law, you need to know we need one initial two boundary conditions, and thirdly, if given a particular situation, right, you need to be able to convert the problem statement into proper, translate the problem statement into proper boundary condition, right? If I say, in this problem, for the ground contamination problem, right, then you should be able to translate, the boundary condition is we have constant concentration here, constant concentration 0 at infinity, right? But if, let's say, we are talking about ground contamination, not in an open soil, we are talking about, let's say, if you like gardening, right? You like to grow strawberries in your backyard in a pot, right? Now you are applying some fertilizer, right? Similar problem. Now the boundary condition will be different, right? Because in a pot, in the Z direction, you don't have infinite space, right? So the fertilizer will hit the bottom of the pot at some point. Then the boundary condition will be different. At the bottom of the pot, it's no flux boundary condition. At the surface, you have constant concentration, right? So this is what I mean. Although I just gave you one problem, but really, you can apply the concept to many different problems, right? But you have to modify the boundary conditions based on the problem statement. Then lastly, we talk about mass transfer coefficients, right? I guess we don't have time now. We can stop here, and I will talk about mass transfer coefficients in next week.